what we're going to be going over here is a learning or an experience curve, and we'll look at a different alternative for calculating our learning curve. So when we're talking about a learning curve, this is where we start with a new process or a new production operation, building a new product here. And we don't have very much experience in building that product or manufacturing that product. But as we build more and more to the product here, we're going to be reducing the time and the cost that's involved in building the product, because we're going to get more and more experience, and it's going to reduce the average time, and we'll look at it in terms of an average time per unit here. It's going to reduce the time it takes to manufacture that product. So just starting out here, looking at a typical learning curve graph, this is where along our x-axis, this is going to be the x, the number of units that produce. So we start out here with 0 units produced, and as we increase our unit production here, we're going to be increasing our learning experience here. So you can think of the x-axis here as your learning experience. You increase the number of units you produced, your learning experience is going to increase here. Okay. And then along our y-axis, we can look at it in terms of the average time or the average cost here per unit to produce that product. And we start out with a high average time here. Let's just say it's 100 units here, or 100 hours to build the first unit here. And as we produce more and more of those units here, we reduce the time that it takes on a per unit versus a unit basis. So what we're doing here, as we reduce our average time per unit here based on our learning experience here, we're going to be increasing our learning proficiency here. So you can think of your y-axis here as your learning proficiency. Produce more units, your learning proficiency is going to increase here. Have a high average time in the beginning, but as you produce more and more of the product, you're going to reduce your average time here, and you're going to be increasing your learning proficiency. So really what we're going to just look at here is really two different alternatives. We have the first case here is where you just use a cumulative average model here, where y equals the cost here, the first unit represented as A, times whatever unit you're building here, raised to some learning rate here, exponent b here, and we'll look at that. And then the other two, and that I'm showing here in red. So that's our normal model that we'd be using here as a cumulative average model, shown in red here, that curve. So that's the normal model that we'd have here. So, but I'm going to look at two other cases here. Really, they're both the same here. We're computer-generated model here, or a curve-fitted model here, and it's going to be for a second-degree polynomial, shown in blue here, which I'm using the same data as I have here for our cumulative average model, but I'm just showing it here on the graph how it tracks compared to our cumulative average or our traditional model here. And that's that blue curve here. And then the other curve is going to be a green curve. It's really the same computer model here, but that's using a different degree of polynomial v cubed here, as I'm referring to it. That's our green curve here, and that tracks along as well here along our red line here, or our cumulative average, our traditional model here. So we'll just look at how we generated this v2 here. That's the second degree polynomial shown in blue here, and the v3 here shown in gray. And then also look at the relationship here to our cumulative average model shown in red here. So we're going to really have this computer model here either as a second degree polynomial v squared here, or as a third degree polynomial v cubed here. So those are going to be shown in green here. And really this computer model is based off some least squares regression analysis. Okay, so that's our typical learning curve here, and we've defined our two different models here. Our traditional model here shown, and then the computer generated models here, or the curve fitted models here, v squared and v cubed. Okay, so that's our learning curve. All right, so let's go and just understand this cumulative average learning model. So this is our basis here, and this is our formula here. It's an exponential function really here. So y here, that's the cumulative average time here per unit, equals a, which is the time required to produce the first unit here, times x. And x is the cumulative number of units that we produced here. And then it's raised to the power here of b, and that's really b here is our really b here is going to be the slope of the function, or some plotted on a log-log graph, and we're going to look at that here. But b is really defined here as log a base 2 for whatever the learning rate is here. So if in this case, our model, the numbers I'm using here is on an 80% learning rate here. So b, our exponent here, equals log to the base 2 of 0.80 or 80% here, and it's going to come with a number you're going to have here for that exponent here, or your learning rate here. This b exponent, or what they refer to as learning rate, is minus 0.322 here. Okay, so that's our traditional model here, our cumulative average learning model, to understand that. Okay, so we'll go down here and we'll just maybe we ought to look at that in terms of what we're talking about here for our traditional model. That y here, that's going to equal, I'm just saying it for the numbers I used here, I just put in 100 hours for a here, the time required to produce the first unit, and then x is whatever units we're producing here from 0 to, in this case I used 20 on the plot that we're looking at, and then b here, that was just our log base 2 here of whatever our learning rate was here. So this is our traditional cumulative average model here. Y equals a times x raised to our exponent b, our learning rate. Okay, so now let's just go and let's understand how we got to our computer fitted model here. Okay, so this is the other alternative I'm looking at here. It's our computer model as an alternative. And really, I'm using MapleSoft here. I use the MapleSoft software here for generating this model. But you could use, there's MATLAB. There's any number of different mathematical software packages you can use here. But it's just based on some least squares and using the curve function here. So using our MapleSoft, let's set up determine what that learning curve is here. So I just put in, just to understand here, for our MapleSoft, I just put with curve fitting. It would be under some statistics package. So if you're looking for something like this in one of those computer math models, our computer math functions, our packages here, just look for something like curve fitting. And then you want to look under something like least squares here under statistics. So what I did here is I just put in the 20 points here that I generated off the cumulative average model here. And then, okay, those were the 20 observations here. These are the actual inputs here. So I just took those right off of the computer, or off what we would have generated off that function that we looked at here, that cumulative average model function here. Just put those in. So that was our input based on that exponential function here. So then the other thing is you have to pick out, like for example, this is after making those 20 entries here, those observations here based on our average time here per unit here. Then you want to just put in, you can check it out on different degrees of polynomial degrees here. So I use the second degree polynomial equation here, and you're going to have like curve this, you're going to fit this data to a curve. It would be some constant here times v squared here, and that's our polynomial here. I'm using v squared as it, plus some other constant a here times our v squared, plus some constant b here times v here, that's a first degree polynomial, plus some constant c here. Put it into computer, enter it, and the computer is going to generate some curve here. This is any of those, you can put any observation into this curve here, and you're going to generate the average time per unit here based on whatever units you're putting out here. You're going to have some constant amount here, some first degree amount here, v for the first v of our first degree polynomial, and then v squared here, a second degree polynomial, some coefficients here. And then just looking at our third degree, I use it at third degree. You can't go overboard with these things here, but just comparing two different degrees here. If I use just a first degree polynomial, it would have been just a linear equation here, and that probably wouldn't be right here. But I started out with a second degree polynomial because we had that exponential function, and then I'm also looking at it as a third degree polynomial. Same thing here, only you're going to have to enter under your curve here, you're going to have some constant times some v cubed here, that third degree polynomial. So you'd add to it the next constant b here times a v squared, the next degree polynomial, then you're going to have some constant times v, the first degree polynomial, plus some constant d here. Then you put that into the computer here with the data you have input here, and the computer is going to give you some generated numbers here. You're going to have some constant amount here. Actually, this is the y-intercept here. And then you're going to have a first-degree polynomial v here, a constant amount here. And then you're going to have added to that second-degree polynomial v squared here. And then you're going to have a third-degree polynomial v cubed here, because we did a third-degree fit here. So what we were using here is some curve fitting, and we fitted that cumulative average model here using our least squares, just to see the comparison, how this curve fitting here works with, compares it to what a traditional modeling here. So what we're going through here is the fact that if, for example, you got some learning curve here, and you for your company or whatever product you'd be working at, maybe it doesn't exactly fit into one of the typical learning models here, cumulative average model, for example here, but you can fit it here using some curve fitting or some least squares analysis here to generate your own model. Okay, so let's just go back and look at those numbers again here. So this was our traditional model here. We'll not go through all those numbers here, but with what we've generated here with our computer fitted alternative here for our second degree polynomial v squared here, we would have gotten these amounts here, just showing it the detail that the computer software package is going to generate. So all you're going to do is, in your computer package here, you're going to put some v quantity in, just like you would be putting some x quantity in here, and it's going to give you some y amount here. It's going to be the average time per unit in this case, based on that cumulative average model we're looking at here. So you would have some amount coming out for your your second degree polynomial, and if you used a third degree polynomial v cubed here, again you'd have some computer curve fitted model here. That's as an alternative, and again you're just putting your units v here as you would put in your units x here to determine y. All we're doing is putting in our units v here. So you'd put whatever v units you'd have here, or x units, you'd put that in here, and the computer is going to give you some generated in this case average time here per unit here, based on whatever v or x quantity you're putting in. Okay, so those are really the computer fitted models. You just have to check out your curve to find out which of the models works the best, what degree of polynomial you're going to put in. First degree, second degree, third degree, and so forth. We have to start out with a second degree because we had an exponential function here. And if you have a learning curve that has a number of different curves or ups and downs in it, you might want to go to a third degree polynomial fit or a fourth degree polynomial fit. Okay, so this gives you one alternative. So if we've gone back to our function here, our curve here, just to understand what's going on to make this comparison. So we went through that computer and we generated our v squared alternative here, or a second degree polynomial for our curve fitted model here. And we have our v cubed one. So just understand here, looking at our second degree polynomial, it's that blue line here again. So it tracks pretty close to our red, or our traditional model here, our exponential function, our traditional model here, the cumulative average model. It's a little on the beginning here, both these v squared and v cubed, they don't have very good results here in the beginning and at the end, because that's just the nature of these different models, but they track pretty close to our standard model here, or our traditional model, cumulative average model here. All right, and then v cubed here, same thing. So you can see they track pretty close here. So the computer modeling here, curve fitting, is doing a pretty good job here. So you have these alternatives. You can either determine in this case we use the average time here per unit. You can either use it going into it. And the idea here with the curve fitting is that maybe the learning curve you have doesn't exactly fit one of these traditional models here, this exponential model here. But you can have the alternative to go in and do a computer analysis here using curve fitting, some statistical analysis to generate your own model here. Okay, and then one other thing here, let's just look at our numbers here in comparison purposes. We see them visually here in the graph here, but let's just go and look at some numbers. Okay, so we've got our output here, our x number of units we built here. And then we got our traditional function here, ax plus b, and then our second degree polynomial fit, and then our third degree polynomial fit. So just looking at an output here of 2 units, you can see it'd be 80 here for our traditional or exponential model here. And then for second degree, 80.7 here, pretty good fit. And then third degree here, it is 83.3 here. Okay, so pretty good estimation here. And then for our output of 4 here, traditionally we got our typical exponential function at 64, our second degree at 69.56, and third degree at 66.89. Still, again, a pretty good fit. And then we come to a unit of 8 here. What do we got? 51.20 here for our exponential traditional model here. And then 52.45 and 49.33 respectively here. So again, pretty good fit here. And then if we went down to, we could track through all of these here, but I'm just showing these different outputs here, these doubling of our outputs here, just looking at those. So then at 16 units, what do we have here? Traditionally, our exponential model 40.96, our second degree at 38.96, and then our third degree fit here at 42.58. Again, pretty good fit here. And then finally, let's just go down and let's look at a log-log plot here. Log-log plot is good to look at because we were working with that exponential curve here. So what you do is on a log-log plot here, again, I've got the learning efficiency plotted against our y-axis here. So as we become more and more efficient here, we're going to increase, as we increase our production, we're going to become more proficient here, increase our learning proficiency here. So we started out with that 100 hours per unit here, and we drive it down as we increase our production. And then again, our learning experience rate here is along our x-axis. So as we increase our output here, we become more learning experience here. We're going to become, our learning efficiency is going to go up. And that is what we're showing here on this log-log paper here. So our traditional model, y equals a, the cost of the first unit times whatever units we have raised to our learning rate exponent here, b here. That's showing in our red line here, and that is tracks real well here because that's the way that function is set up here. It's really a straight line down here. And in this case, you're looking at the slope here. You're really looking at these log-log functions. You're looking at the slope. That's the rate of progress here. And the slope that, based on an 80% learning curve, we would have calculated our learning rate here, exponent b, at minus 0.322 here. But just looking at our other functions that we looked at, our second degree polynomial v squared here, that's that blue line here. So that tracks in. It's not bad. Again, you can see here at the beginning it doesn't really fit with the red line here, and at the end it probably doesn't fit that well here. But nonetheless, it gives us an alternative. So if our exponential function y equals ax plus b didn't fit our model, we can at least go and we can set up our learning curve here based on some exponential fit or in a computer generated model here. So v squared, that was our blue line here. And then v cubed here, looking at the third degree polynomial fit, was the green line. Again, not bad. It's fitting right in here. So I guess what you're looking at here when you're doing these different model fittings, and you're going to be using some alternative model here for like curve fitting, this least squares, you want to look at the different degrees here and make a comparison between the different degrees here in your polynomial, either depending on the function that you're looking at here for your learning curve, and see which one of those two are. In this case, I did a second degree and a third degree fit. You'd have to make a selection. I kind of like this third degree fit here in a way. And the second degree isn't bad here compared to our standard or our traditional model here. So nonetheless, here in this log-log plot here, what it's really telling you is you can look at it in terms of your learning proficiency here along your y-axis here and your learning experience along your x-axis. So your proficiency, you become more and more proficient here, or you're going to be driving down your unit costs here as you gain more experience here. But log-log function here is really looking at, you're going to be looking at different alternatives here, and you're looking at the slope or the rate of progress here, and you'd be looking at them. In this case, since I've run the v squared here and the v cubed against our same amounts that I had here for a y here, so they're sort of the same here. You can see that. But nonetheless, you can see you do have a rate of progress here. That's just looking at a rate of progress, or your slope here is pretty comparable between all the standard or our typical exponential cumulative average model here and our curve fitted here for the second degree polynomial and the third degree polynomial. All right, just an alternative here. We just went over the different numbers here and looked at a different alternative that you might use here when you're starting to calculate learning or experience curves. Okay, so that'll summarize our discussion.